Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. This is part 3 of the sequential circuits. We are going to learn about the flip-flops here. In the last two sessions, we discussed sequential circuits which use the memory elements. They are classified into two synchronous and asynchronous sequential circuits. The flip-flops and the latches are used to build the synchronous and asynchronous circuits respectively. We have covered the latches in the previous sessions. Now it is our turn to learn about the flip-flops. In the previous sessions, we had come across the term flip-flops. I had mentioned that the flip-flops are binary cells which can store one bit of information. They hold this value and becomes the memory of that sequential circuit. Moreover, these flip-flops are stable and predictable because they change their output only at discrete and regular intervals of time. What does the term discrete indicate? The literal meaning of the term discrete is separate and distinct. To understand this, see the picture of analog and digital signals. You can make out that the analog signals are continuous. They occupy some state of or value at any point of time. The digital signals are different. They are at the level 1 at one point of time and moves to level 0 at the next point. You can accurately specify the values of digital signals at any point because of their discreteness. Another example is the analog watches and digital watches. In analog watches, the seconds hand will be spinning around a dial always, hence it is continuous, whereas in the digital clocks the time is accurately displayed in numerals and it has discrete values. By now you might have understood the difference between continuous and discrete, and hope you are clear about what exactly discrete means in this context. We are discussing about the predictable behavior of flip-flops, that is due to their response to the clock pulses at discrete intervals of time. They differ from latches in this aspect. The latches does not depend on any clock pulses. They change their value as and when their input changes. This attribute contributes to the unpredictable behavior of the latches. Hence, latches are used in asynchronous sequential circuits which does not have to do anything with time. The flip-flops on other hand are used in synchronous sequential circuits, and synchronous circuits relies heavily on them. And the essence of the time is brought into the picture using clock pulses. Now, what are these clock pulses? They are signals with changes in the voltage occurring at regular intervals. These clock pulses triggers the changes in the output. Triggering means you are making something happen in the circuit, or in other words we are controlling the circuit using certain signals. So, this is about the general behavior of flip-flops. So, to summarize, flip-flops are circuits which can hold one bit of information and they are triggered using the clock pulses. Let us move on to the more specific details now. What are the inputs and outputs of flip-flops? Flip-flops take one or two inputs which are binary values, and on the trigger of a clock pulse it will store the resultant value in the flip-flop after some processing. It has two outputs, one is the stored value and the other one is the complement of that value. In short, flip-flop is a device with two stable states, either the binary 1 or the binary 0, and the most useful characteristic of the flip-flop is that they continue to remain in that state until triggered into the other, and thus brings the memory into these circuits. Now, let us look at this part, how is the value entering into the flip-flop. It can be done in many ways, and this difference gives rise to various types of flip-flops. We We are going to learn about the types of flip-flops and how they behave in the coming sessions. The first flip-flop we are going to see is SR flip-flop. It is a basic flip-flop circuit. Flip-flops are the improved version or modified version of SR latches, and if you know the working of SR latch, then it is very easy to understand the working of SR flip-flops. If you have not watched the previous videos on sequential circuits, please do watch it before this clip to have a better understanding of SR flip-flop. Let us see the block diagram of a SR flip-flop first. Similar to SR latch, the SR flip-flop has two inputs, set and reset, and has two outputs, Q and Q complement. If you are familiar with SR latches, you might have noticed that there is a third input, which is the clock pulse, which was not present in the latches. Now, let us see the construction of SR flip-flops. As mentioned earlier, the flip-flops can be constructed from two NAND gates or from two NOR gates. Let us see the SR flip-flop constructed using NAND gates first. Look at the picture. The flip-flop has some additional gates. They are using two NAND gates to which the inputs S and R are connected. Along with these inputs comes the very important signal, the presence of the clock pulse. Since there are 4 NAND gates, we will number them as 1, 2, 3 and 4. The first two NAND gates are connected to the input of the flip-flop and last two NAND gates are connected to the outputs of the flip-flops. The first two latches forms the steering gates of the circuit because it steers the changes in the output, and the last two forms the SR latch using NAND gates. As I told you, the flip-flops are nothing but a modified version of latches. To understand the behavior of flip-flops, you should be knowing how a NAND gate works. Recall that a NAND gate produces 1 when any one of its input is 0. Here there are 3 inputs S, R and CLK. The 3 inputs will derive 2 raised to 3 combinations, that is, there will be 8 different input states to this flip-flop. Let us see each one in detail. Before I start explaining the working, let us have a look on the SR latch characteristic table and its logic diagram. Recall that when an SR latch built using NAND gate, a 0 at S input sets the circuit, a 1 at S input resets it. If both inputs are 1, they continue to hold the previous value. A 0 at both inputs leave the circuit in an undesirable state. Here is the first input combination. Assume that clock equal to 1 or the clock pulse is positive. If S equal to 0 and R equal to 1, then NAND gates 1 and 2 now produces a 1 and 0 respectively as its outputs. That is, now the SR latch with NAND gates 3 and 4 will have S equal to 1 and R equal to 0. Please see the picture. Now recall the truth table of SR latch. For such values of S and R, the output of the latch will be Q equal to 0 and Q complement equal to 1. Since Q complement is 1, we can infer that when set input is low, the flip-flop goes to the reset state. That means when the initial input of set is turned out to be 0, it made the flip-flop to reset by setting the Q as 0 and Q complement as 1. In the next case, let clock equal to 1 and S equal to 1 and R equal to 0. Now the gates 1 and 2 will produce 0 and 1 as their outputs as per the working of NAND gates. Now the inputs to the SR latch are S equal to 0 and R equal to 1, which turns the Q to a high state and Q complement to a low state. Or in other words, we can say that when the set input was high or 1, the flip-flop went to the set state by setting Q as 1. In the third case, when the input S and R are 0, the clock is 1. The inputs to the SR latch becomes 1 at both the gates. This is because any input of 0 at the NAND gate produces an output 1. So, as per the truth table of SR latch, when the inputs S and R are 1, the current state of the circuit will be the previous state itself, even though there was a change in the input. Or we can say the previous value is latched inside the circuit. So, when the inputs S and R are 0, no change of value happens inside the circuit. So, let us infer that when both the inputs to a SR flip-flop is low, the circuit retains its previous state by latching the value inside. In the fourth case, the inputs S and R are 1 and clock is also 1. Since all the input values are 1, the NAND gates produce a 0 as its output. Now, both the inputs to the SR latch become 0, which will lead the circuit to have both outputs as 1. This is an invalid state and should be prohibited because it violates the condition satisfying the output value. So far, all the outputs produced by the flip-flops were complements of each other. But in this case, the output values are the same, they are not the complements of each other. We call such a state as indeterminate state because either set or reset state may follow as the output depending on which 1 bit value at the set or reset input remains longer. This output cannot be predicted at all since it depends on the state of the hardware used and hence should be prohibited in the design of flip-flops. Now, let us keep the clock pulse as negative or 0 and check the 4 scenarios. The first case is when S equal to 1 and R equal to 1. Since clock is 0, both inputs to SR latch fails at 1. When S equal to 1 and R equal to 1, the SR latch does not change the previous state. That is, even the inputs are changed, the clock pulse which is 0 at this time did not affect the state of the circuit. It remained in the previous state itself. In the second case, let S equal to 0 and R equal to 1. Since the clock is 0, we will have both inputs to the SR latch as 1. And again the change in the input will not affect the output, it still remains in the previous state and the reason for this is the clock pulse is 0. In the third and fourth case, the same scenario results. Since the clock signal is 0, it turns both inputs to the SR latch to 1 and keeps the previous value intact in the circuit. Did you notice an important point here? When the clock was negative, it did not affect the current state of the circuit at all, but it remained in the previous state itself. Or in other words, the circuit responded to the change of inputs only when the clock had a positive signal. This is why we emphasized that flip-flops are stable, they are predictable and they only change their input only at regular intervals of time and a clock pulse trigger them for this change. Now, let us turn our attention to the SR flip-flops designed using NOR gates. See the picture? Here we are using 2 AND gates additionally and connecting them to the NOR-gated SR latch. This circuit also has steering gates which are nothing but the AND gates. And this steering gates steers the inputs to the SR latch constructed using NOR gates. Since we are using AND gates as steering gates, let us memorize the working of the basic logic gate AND. As per the property, AND gate produces 1 only when both their inputs are 1. Rest all the cases it is 0. Let us assign values to the input and see how the NOR-gated SR flip-flop works. Again, Here are 3 inputs which will result in 2 raised to 3 equal to 8 combinations. We will consider the combinations where the clock pulse is positive. See the first combination. Before getting into the working, please recall the working of an SR latch using NOR gates. To refresh your memory, please see the diagram and characteristic table of SR latch using NOR gates. Assume that clock equal to 1 or the clock pulse is positive. If S equal to 0 and R equal to 1, AND gates at the input now produces a 1 and 0 respectively as its outputs. That is, now the SR latch with NOR gates will have S equal to 1 and R equal to 0. Look at the picture. Now according to the truth table of SR latch, for such values of S and R, the output of the latch will be Q equal to 0 and Q complement equal to 1. Since Q complement is 1, we can say that when set input is low, the flip-flop goes to the reset state. Because the initial input of set was 0, it made the flip-flop to reset by setting the Q as 0 and Q complement as 1. In the next case, let clock equal to 1 and S equal to 1, also R equal to 0. The AND gate will produce 0 and 1 as their outputs as given in the picture. Now, the inputs to the SR latch are S equal to 1 and R equal to 0, which turns the Q to a high state and Q complement to a low state. Or in other words, we can say that when the set input was high, the flip-flop went to the set state by setting Q as 1. In the third case, when the inputs S and R are 0 and clock is 1, the inputs to the SR latch become 0 at both the gates. So, as per the truth table of SR latch, the current state of the circuit will be the previous state itself, even though there was a change in the input. Or we can say the previous value is latched inside the circuit. So, when the inputs S and R are 0, no change of value happens inside the circuit. In the fourth case, the inputs S and R are 1 and clock is 1. Now, the inputs to the SR latch becomes 1 at both gates, which will lead the circuit to have both outputs as 0. This is an invalid state and should be prohibited because the outputs obtained are not complements of each other. We call such a state as indeterminate state because either set or reset state may follow depending on which one at the set or reset input remains longer. This output cannot be predicted and hence should be prohibited in the design of flip-flops. Now, if you set the clock to be negative, then as per the truth table of AND gate, if any one of its input is 0, then it will surely produce 0 as its output. Then you will have both the inputs to the SR latch as 0, which keeps the circuit to retain its previous state. Or we can conclude that no change to the flip-flop happens when the clock pulse is 0 or low, even if the input to the circuit changes. So, we have learned about SR flip-flops and how they are constructed using NAND and NOR gates. Next, you are going to see two different tables which will help you to understand their working better. The characteristic table. This table summarizes the operations of flip-flops, that is, when the inputs are given, how the flip-flop behaves can be interpreted from this table. Look at the table here. The values of S and R when clock pulse is positive is given here. The output is denoted as Q of t plus 1, which corresponds to the next state of flip-flop after applying these values as the inputs. In brackets, I have given the states of the flip-flop when they fall into after applying these inputs. When S and R are 0, the next state of the flip-flop will remain the same, it will not be changed. When S equal to 0 and R equal to 1, the flip-flop will be reset, and when S equal to 1 and R equal to 0, the flip-flop goes to the set state and both the inputs are 1, they will remain in an indeterminate state. So, we are coming to an end. To wrap up, in this session we covered about the general characteristics of flip-flops and learnt in detail about the basic flip-flop, the SR flip-flop. We learnt the significance of clock pulse in the working of flip-flops and understood that the behavior of flip-flop changes only when the clock pulse is high and remains in the previous state when the clock pulse is low, irrespective of the input changes. Finally, we saw the excitation table which summarizes the operations of flip-flops. Hope this session helped you to understand the concepts of flip-flops in a better manner. See you in the next session with a different flip-flop. Thank you.